In this section, we're going to talk about prime factorization. What that means is, given a number like 6, you want to write 6 as a product, but the factors have to be prime numbers. So the prime factorization of 6 is 2 times 3. Now, the prime factorization of a number is unique up to the order that you write the numbers in. In other words, I could have written this as 3 times 2, but it's still the same 2 prime numbers. 18 you can think of as 6 times 3. 3 is prime, but 6 is not. We can write 6 as 2 times 3, and don't forget to multiply by the other 3. This is the prime factorization of 18. You can write it like that. Or you can write 3 squared times 2. The order doesn't matter. One of your classmates may say, you know what, 18 is 9 times 3. Oops. And that would be wrong, of course. But another classmate can say it's 9 times 2. Say 9 is not prime. It's 3 times 3 times 2. Now all of those 3 numbers are prime. And they're the same 3 numbers I got up here. Got 1, 2, and 2 3s. Same thing. It's unique. For example, if you had 50, somebody may say, oh, that's 2 times 25. 2 is prime, but 25 is not. 25 is 5 times 5. And those numbers are prime. In fact, all 3 of them are prime. We found the prime factorization of 25. Another student can say 50 is 10 times 5. And of course that student would be right. But 10 is not prime. It's 2 times 5, and it happens to be that 2 and 5 are prime, times the next 5. If one of these numbers were still not prime, I would continue and write down how to factor that number. In any case, we get 2 times 5 squared. We got the same answers. Somebody may say, is there some kind of a method to do this with? The answer is yes. And hopefully, as expected, the method is not unique. What you want to do is write down 2 numbers that multiply out to 60. The rule is only one rule. Don't use the number 1. Use any other number. For example, somebody may say 60 is 10 times 6. That's fine. Since 10 is not prime, we continue with the tree. And we write 10 as 2 times 5. 2 and 5 happen to be prime, so we stop there. But 6 is not prime. That's why I didn't circle it. 6 is 2 times 3. And those numbers happen to be prime. So 60 is 2 times 2. You don't have to put it in numerical order, but I will. Times 3 times 5. Another student could have said 60 is 15 times 4. 15 is not prime, so I'll break it down. Just don't use 1. And 15 is 5 times 3, and those happen to be prime. 4 is 2 times 2, and those are prime. Once again, we got 2 2s, a 3, and a 5. Somebody could have said 60 is 20 times 3. 3 is prime. 20 is not. 20 is 5 times 4. 5 is prime. 4 is not. It's 2 times 2. If you notice, we got 2 factors of 2, 1 factor of 3, and 1 factor of 5. Now, I want to point out something. Doing this tree is very, very helpful. And a lot of students, they just do the tree, but they didn't answer the question. The question is, write 60, find the prime factorization of 60, which means write 60 as a product of just prime numbers. If you don't include this, in my opinion, you didn't do the problem. You didn't even write down an answer. If you just have 60 equals and it's blank, you didn't write down. You have to give it your best shot. Multiply some numbers that multiply out to 60, and those numbers should be prime. 2 times 2 is 4, times 5 is 20, times 3 is 60. Those numbers multiply out to 60, and they are prime. This is an attempt at writing the answer, and it happens to be correct. Not writing down what 60 equals, you're not answering the question. Okay? What I'm getting at is this student would get 100% of the points on the problem because the student wrote 60 equals that. They would get 100% on the problem. Depending upon what mood I was in, I can give this person no percentage. They didn't write down any answer. You know, maybe I'll give them 80% because they did do the factor tree. But understand, the factor tree only helps you get the answer. It is not the answer. The answer is writing 60 as a product of prime numbers. Since 2 is squared, since 2 is prime, 2 squared is a product of prime numbers. 2 times 2, which is 4, times 3, which is 12, times 5, which is 60. Now we are multiplying just prime numbers. I'm not saying 4 is prime, but we're thinking of 4 as 2 times 2 times 3 times 5. Those are 4 prime numbers, and they multiply out to 60. Okay, if one wants to be very unnice, assuming the student didn't write this, they can give 0 points because the student didn't even answer the question. You know, an answer might be, 4 times 15. At least they put an answer. And then the teacher can say that's not prime and that's not prime. But at least they put an answer. Don't do all your work and not put an answer. All your work means this factor tree. Let's try prime factorization of another number. Say a big number, 296. It's even. I know 2 goes into it, and 2 is prime. If you don't know how many times, on the side you do 2 into 296, you get 148. Okay, 148. That's not prime. You can say it's even. So it's 2 times 74. 2 is even. 74 is not. It's 2 times 37. 2 is prime, and so is 37. So it's 2 cubed times 37. 1, 2, 3 2's. Another student can be slick and say, you know what? I know that 300 is 75 times 4, but 296 has one less 4, so it has 74 fours. This is 74 times 4. 74 is 2 times 37, and both of these numbers are prime, and 4 is 2 times 2. Once again, we have 2 3s times 37. Or another student could say that this number is 37 times 8. 37 times 8. And 37 is prime, 8. Now, if you see 8 is 2 times 2 times 2, that's okay. You can put 3 branches. There's nothing wrong with that. It's typical to put 2 branches. That's how generally it's taught, but there's absolutely no reason why you can't put 3 branches. If your teacher says no, tell your teacher they don't know what they're talking about. Okay, in all 3 cases, we got the same answer. Let us try one more number. Suppose we have 300. These are not unique steps. People can arrive at the same answer up here, but use different steps. One may say 30 times 10 is 300, which is true, but 30 is not prime. You can say it's 5 times 6 or 10 times 3. 5 is prime, 6 is not, it's 3 times 2, and that's prime. 10 is 5 times 2, and those are prime. So you have 2 times 2 times 3 times 5 times 5. The bases are all prime. That's all it takes. Another student could have said, I know my 100 table, 100 times 3 is 300. And coincidentally, 3 is prime. Then they can say 25 times 4 is 100. 5 times 5 is 25, and those are prime. 4 is 2 times 2, and that's prime. Once again, we have 2 factors of 2, 1 factor of 3, 2 factors of 5. Yet another student can say, what are you talking about? 300 is 75 times 4. 4 is 2 times 2. 75, that's 3 times 25. 3 is prime. 25 is not, it's 5 times 5. And those 5s are prime. 2 factors of 2, 2 factors of 5, 1 factor of 3. 2 factors of 2, 1 factor of 3, 2 factors of 5. Notice we get the same answer. Prime factorization is unique up to order. What does order mean? Somebody can say it's 3 times 5 squared times 2 squared. They're only using primes. Up to order, it is unique. Let's try just one more. Suppose you have 400. Somebody can say, I know, that's 20 times 20. 20 is 5 times 4. Just like that, 20 is 5 times 4. 4 becomes 2 and 2, and the 5s are prime. So are the 4s. So we have 2 factors of 4. Let's try that again. We have 4 factors of 2. 1, 2, 3, 4. And then 2 factors of 5, which becomes 5 squared. There is your prime factorization of 400. Just try it a couple of more times. Another student can say it's 100 times 4. None of those are prime. So break it down. 100 is 10 times 10, or 20 times 5, or 25 times 4. 4 is not prime, it's 2 times 2. Now the 10s can be reduced to 5 times 2, and those are prime. 5 times 2. And in the end, we have 1, 2, 3, 4 factors of 2 times 1, 2, 2 factors of 5. Another student can say 400 is even. It's 2 times 200. 2 is prime. 200, well, is 2 times 100. And 100 is 25 times 4. 25 becomes, hold on please, the 25 should not be circled because it's not prime. And 25 factors to 5 times 5, and those are prime. And 4 is 2 times 2. And once again, 1, 2, 3, 4 factors of 2 times 1, 2. 2 factors of 5. We get the same answer. As long as we don't make a mistake, we get the same answer regardless of how it's done. The factor tree method is not unique. First row, 20, 20. Here, 104. Here, 100. Here, we had 4 numbers. 5, 4, 5, and 4. Here, we also had 4 numbers. Look at this. Here, we have only 2 numbers because one branch already died. Here, we have a branch with 4 numbers. Here, we also have 4 numbers. Here, we just had 2 numbers. No more branches here or here, but here, we had a branch with 4 numbers. Okay, it's not unique. But what is unique is the final answer. Just know your times table. Don't ever use 1. If you have 39, don't say it's 1 times 39. You didn't get anywhere. And if you did do that, do not circle 1 because it's not prime. Nor can we write it as a product of prime numbers. I guess the 1 would just stay there. And then say 39 is, say, 13 times 3, and these are prime. 13 times 3. You know, you should have just done 13 times 3 and be done. Okay. Don't use 1 because whatever this number is, the tree with 1 just dies because it's not prime, so it doesn't get circled, and you can't write it as a product of primes. So you're just back dealing with 39 again. You didn't get anywhere by doing the 1. Okay, that completes the section on prime factorization. Don't forget, if you use the factor tree, that's excellent. But make sure you answer the question.